Hi, I'm Aditya, and today I'm going to be going over hidden Markov models. Here's my Jupyter notebook that goes over a brief summary of what hidden Markov models are, how we can use them in bioinformatics, and later how we can use them in bioinformatics to predict promoter regions or places of higher gene expression. First, we'll start off with the library imports. To optimize the coding process, I used a bioHMM hidden Markov model. And I've imported two different parts of this library, the hidden Markov model and a Markov model builder, which I'll show you later in the code. The thing I implemented next was this bioseq library, and this was used for defining biological sequences through code. So for instance, if I wanted to define a nucleotide sequence of A, T, C, G, CTG, I can define that as a sequence so that the bioHMM model can parse through it such as that. Next, I use the NumPy library to look through different arrays and also manipulate different arrays, and then I use RE or regex expressions to filter through different expression data. So first, I'll start off with what a basic hidden Markov model is. So this is an example of a Markov model. So there's three major things you need to know about a Markov model and its probabilities. So we first start off in a start phase, and then we go into different states. So these different states are what is actually occurring. So this can be something that's like in the sky, right? For instance. So we're looking at the weather over here. So we have rainy and sunny. So when we start off, we have a 70% probability of starting off as sunny, as seen by this arrow pointing to sunny. But we also have a 30% probability of starting off as rainy, as seen by this arrow over here. And then we see these arrows that are pointing in between rainy and sunny. So what does this mean? So over here, this arrow pointing right back to sunny means that there's an 80% probability of going right back to sunny. So in your next step, you would have sunny, and then there'd be an 80% probability of you moving to sunny again. And there's a 20% probability of you moving from sunny to rainy. Similarly, for rainy, you have a 40% probability of moving back to rainy in the next stage. And then you have a 60% probability of moving from rainy to sunny. Now, what are these walk, shop, and clean that we see over here? These are things called emission probabilities. So over here, we're saying that if it is a rainy weather, then a person is likely to do one of these three following actions with a variety of different probabilities. So for instance, if it's rainy, it would be 10% chance of walking, 40% chance of shopping, and 50% chance of cleaning. If it's sunny, that means you have a 60% chance of walking, 30% chance of shopping, and a 10% chance of cleaning. Now, what's the reason for creating these hidden Markov models? So one interesting thing that actually occurs from these is that if we're given the sequence of walk, shops, and clean, so for instance, through a sequence of a couple of days, if a person walks for maybe 3 days, then we can notice that the most probable weather states that are there are likely sunny, 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 for instance. And essentially, a hidden Markov model allows us to do this by looking at all these different probabilities and calculating a probability score for different probability estimates. And this will allow us to essentially predict these hidden states when we're given these emissions. So let's first start off with a more basic example. How do we actually code up these hidden Markov models? So first, I defined some parameters. So we have the transition alphabet, which is rainy and sunny. So these are our states. Then we have the emission alphabet, which is WSC, or walk, shop, and clean. Next, I define the initial probabilities, or the probabilities that they are initially defined to, which are 0.3 for sunny, rainy, and then 0.7 for sunny, as you can see over here. And this is just defined as a regular dictionary. And then with the transition probabilities, where the key is a tuple going from one state to the next state, and then the value is actually the transition probability. Lastly, we have our emission probability, which again is defined similarly as a tuple, and we have the different probabilities for our emissions. There are two different ways to build this. I'm going to be talking quickly about the Markov model builder, and then I'll be talking about the hidden Markov model builder. As we mentioned over here, these are the different types of ways we can build a hidden Markov model. So the first way is essentially we build first with the transition alphabet and the emission alphabet, and then afterwards we set the initial probabilities by setting this dot set initial probabilities, and then we do dot set transition score and dot set emission score. So essentially, as you can see in the hidden Markov model, we can do all this in one step, but in this step we have to do them in sequential order. And this Markov model builder is essentially just for looking at how a Markov model we built without actually doing anything with it. So this is just a class built for just specifically viewing a Markov model, while a hidden Markov model, the second one, is used more for computations. So as you can see over here, we've defined a hidden Markov model with these different parameters. So the transition alphabet, the emission alphabet, the initial probability, the transition probability, and the emission probability. And lastly, these last two parameters are just pseudo-counts. So these are just these are something that we don't need to worry about. We can just set them as 1 for now. And then next thing we do is run this thing called the Viterbi algorithm. And again, like I was mentioning before, what we can do with these hidden Markov models is actually determine the optimal hidden state configuration for a particular emission state combination. So for instance, if we have walk, shop, and then clean as our different emissions that happen over a set of, like, let's just say 3 days, then our different states will be sunny, sunny, and rainy. And we can say that it has approximately a probability of 10 to the negative 4.97 probability of happening. And although that seems like a very small number, note that these numbers are pretty small. So they're all 0.4, 0.3. And if you multiply these over a bunch of different days, you'll realize that these numbers actually become really small over time. So that's essentially the first part. This is how we build a Markov model. But how do we actually use this in bioinformatics? So we're going to start off by looking at GC-rich regions. And this essentially is regions where we're trying to differentiate background from promoter regions using the primary nucleotide sequences. So our emission probabilities are ATCG, and our states are background and promoter. Over here, as you can see, we have the two states of background and promoter. And similar to what we had before, we have the transition probability. So 85% of staying in the background, 75% chance of staying in the promoter. And then we have 15% chance of going from background to promoter and 25% chance of going from promoter to background. And then we have the different emission probability. So we have 25% for all these in background. But for promoter, we have a higher probability towards those in the GC regions. And note that the initial probabilities are defined as 0.5 because there's an equal chance of them being in the background or promoter region at the beginning. So over here, we just defined these different values as mentioned earlier. And then we ran a Markov model, and I similarly ran the Viterbi algorithm. So over here, for a sequence of H, G, T, A, C, A, C, T, G, G, T, we can see that they were all predicted background regions. So there was no predicted promoter regions. Over here in a similar sequence, G, C, A, 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 T, G, C, there's all background regions again. But over here, in a region with a lot of GC content, as you can see over here, there were actually regions of promoters. So there were predicted promoter regions, and we can see that the probability that it was actually predicted to be a promoter region in a log transformed way. Alright. And the last thing we're going to be talking about with regards to HMMs is dinucleotide sequences. So how can we actually predict HMMs while keeping regards to the last nucleotide in the sequence? So our last analysis looks at HMMs with memory, where the value of the last nucleotide determines the value of the next nucleotide. So HMMs by definition are usually memoryless. So what we're going to do in this code is define 8 different transition states of A, C, G, T. And they can either be background, which is a negative sign, or they can be P, which is a promoter sign. And essentially what we're doing over here is we're getting combinations of all of these different possibilities. And then these are all the different states, and we're mapping each of these to different emissions. So over here, we define all the initial probabilities as 0.125. And then transition probabilities have actually been estimated in a paper by Durbin Eddy et al. 1998. So over here are the probabilities that have been defined by Durbin Eddy et al. So for instance, this is the probability of starting off at A plus and going to an A. This is the probability of starting at A plus and going to a T, and so on. And lastly, we have, when we're going to A plus, we can either go back to A plus or we can go to A minus. So one thing that we were looking at also was that there's a 75% chance of going from promoter to promoter, 25% chance of going from promoter to background, 15% chance of going from background to promoter, and 85% chance of going from background to background. So as you can see over here, this is similarly just the transition probability that we've seen over here. So this is the exact same thing that we've been working with before. But now what we're doing is we're essentially saying that if the probability going from A plus to A was 0.18, and the probability going from A plus to A plus is just 0.75 times 0.18. So that means it would just be 0.135, and the probability going from A plus to A minus is just 0.045. So that's essentially what we did over here, and this is how we define the different values inside of the hidden Markov model. And lastly, the emission probabilities are defined such that if we're at an A plus or an A minus, that means that the probability of it emitting an A is simply just 1, because there's only other one probability can emit if it's a A plus or an A minus state. Similarly for C plus, C minus, G plus, G minus, and T plus, T minus, that was similarly done. And then once again, we ran the hidden Markov model and we ran the Viterbi algorithm on it. So we have a sequence which is defined over here. So it's A, G, T, A, C, A, C, T, G, G, T. And over here we can see that this is the following promoter regions that it has determined. So over here, it's determined that there are promoter regions of minus, 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 minus. So it means, again, it's all background. This is very similar to what we've been seeing over here. So this is the same sequence as over here, and it's given all backgrounds. So these minuses just essentially mean that it's a minus region. And as you can see in the sequence, it follows the same exact values as seen over here, which means the emission probabilities are 1. Lastly, what I did was create a Viterbi coding implementation. So I was looking at how exactly we can look at the Viterbi algorithm, not just as a method, but actually how we can break it down. So I'm going to quickly go over my coding implementation and how you can implement one yourself. So first thing we're going to look at is actually what is going on over here. So over here, we have a dynamic coding implementation of the Viterbi algorithm. So we see this v variable being defined over here, and that's essentially what's being printed out over here. So these are the different steps that are inside of the Viterbi algorithm. So over here, we can see that it starts off at G plus, because if we look at our sequence above over here, it starts off at A, and that means that there's going to be a G plus that's most likely to occur from an initial probability standpoint. So this just chooses. So this shows that there's either a G plus or there's a G minus that's going to occur most likely, because there is a G sequence that is starting off first. Then next, what happens is that it looks through all the various possibilities that can occur in the next phase. So it looks at all the different transition probabilities for G plus and G minus. So for instance, at G plus, it looks at its transition probabilities with all the plus states and all the minus states, and it looks at which is the most optimal probability for actually occurring. And it's the same thing for G minus. So that's essentially what's happening over here. So it's multiplying the calculated probabilities, the next step, and transition probabilities for the first state, and then finds the maximum across all the states by multiplying the calculated probabilities by the transition probabilities. And essentially what it's doing here is finding the maximum probability for each of these states. And then after that, it stores those maximum probabilities inside of V. So this is the next stage. So let's see that C plus is the most optimal to occur next, and also C minus might be the most optimal to occur next based on different probabilities that we've seen in 0. And it does this over and over and over again until we finish the sequence. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 different states over here. So this is the initial state, and then it goes through 9 different iterations, as you can see over here. Okay, so the last thing over here, as you can see, is it goes through all of this, and this is essentially a pointer matrix. And if you're familiar with dynamic programming, what we have to do after that is create a traceback mechanism to actually find the probability of the last state. So we find the maximum probability of the last state, and then we trace back and find the maximum probabilities across all states. So for instance, if we start off at a maximum probability over here, so this is A minus over here, as you can see, then it'll see that the most optimal probability after that is A plus. So it'll keep going backwards in the sequence and finding the most optimal probabilities for all the states and looking at previous to determine the most optimal pathways. Lastly, this DP table is essentially there to create this table. So we just use the DP table to print out various lines so you can view this. And then lastly, we use the structure to change the transition probability from something seen over here to something that's more readable by this command. Okay, and lastly, what we did was look at different Viterbi algorithm implementations. So we looked at the hidden Markov model implementation, which gave G plus, C plus, G plus. So we give plus, 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 minus, minus. So that means there's promoter regions and then a background region. And then, as you can see, our implementation with the Viterbi algorithm by itself also gave promoter regions over here, but it noted that this C region was also negative. So as you can see over here, using dinucleotide sequences or using mononucleotide sequences or using your own implementation all give different values. It's just a matter of what exactly you are trying to do. And as looking at these different models, I've noticed that a dinucleotide sequence approach is actually the best approach, and using a combination of your own coding implementation and also this type of hidden Markov model will produce the most accurate results for predicting promoter regions. For more information, look at my GitHub over here, which goes into detail of all my code and also stores all my details so you can fork it and look at it later. And I also wrote a quick article discussing the different Markov model things. Thank you for listening, and I'll see you next time.